This is chapter 8, all about gases. And so the first image that I want to show you here is this little boy drinking out of this really long straw. And you can see that the molecules of the air, they're showing the molecules of the air pressing down into the outside of the soda. And you see a little arrow where the liquid is going up. So thinking about this, how long do you think a straw could be and you could still get liquid up the straw? We're going to explore how this happens through looking at gas laws, and we'll answer this question a little later. So the first thing we have to talk about is the kinetic molecular theory. And so kinetic molecular theory meaning the movement of molecules, the kinetic meaning the energy of motion. So kinetic energy is the energy of motion. And so we're looking at the motion and the energy of molecules, and that's the theory behind it. We're going to have several postulates or points to this theory, assumptions that we should make, but first we're going to check out a quick simulation. Okay, so in this simulation, which is linked in the slides, you can look at that. We're going to look at what happens as we heat up particles and how they behave. So the first thing that we're going to show is the kinetic molecular theory. And again, there's going to be more slides to talk about these different points. First, we're assuming all matter is composed of tiny particles. Those would be atoms and molecules. That these particles are in constant motion, and that the amount of motion is proportional to the temperature. So increased temperature means increased motion, and we know this because temperature is a measure of the average kinetic energy of the sample. Solids, liquids, and gas differ in the freedom of motion of the particles and the extent to which the particles interact. So here's a typical image of a solid in a textbook. Now this image of a solid shows very little space between the solid. It shows them kind of packed in together. But this image is not quite exactly what a solid would look like, because we're usually looking at maybe paper images or still images. With a simulation, we can really see what a solid looks like. So here's a real kind of image or a little movie of a solid. Solid particles are moving. They are vibrating constantly. And so thinking about that, the chair you're sitting on, the hair on your head, the clothing on your body, everything is kind of vibrating a little bit and moving around like this, and that may make you feel a little itchy with your thinking about all those things that are moving around you. And the only temperature at which you can get things to stop moving is absolute zero, and that is that 0 Kelvin temperature. And so moving forward in the simulation, if I were to try to speed it up a little bit, so what happens to a solid as I speed up the particles? Well, they start moving faster, right? And eventually I'm going to get into a point of starting to melt the solid. And so we know from chapter 3 that there are points in heating something at which you actually get melting or vaporization or boiling. But there are also times which you're heating something and just making the particles go faster. So if we start heating it, we start to make the particles go a little faster. And so you can see we're still a solid here. We're still tightly packed. It's just now everything's moving faster. And so then as soon as we heat it enough, it will start to expand to become a liquid. And so now if we're in the liquid part, we don't see, there is more space. It's kind of hard to see because the particles are moving so fast. It's hard to see those space, but you can see that our little particle here, the one that's a little darker, is moving around a lot freer. So the range of motion in a liquid is a lot more. If I were to even increase the speed more of a liquid, then eventually we would get to a gas. But before we move there, I want to explore the area right at the top of every liquid. So at the top of a liquid, you have this kind of, we call it an equilibrium, a back and forth of liquid particles jumping out to become gas particles. And these gas particles create a vapor pressure. And so they create some kind of gas pressure at the top of all these containers. And so we call that vapor pressure. Eventually, once I get into a gas, I can look here. I probably looked at it for 10-15 minutes and cannot find our little friend that we were looking at previously because gas particles are so far apart in a gas. Particles are so far apart in a gas that you'll never run into another gas particle right until you maybe hit them and then you'll be knocked away. And so actually this is a little incorrect. It's kind of showing you the interactions, but realistically you should probably see only one gas particle at a time because they're so far apart. Okay. And feel free to play with the simulation again if you want to. It is linked in your slides. So the kinetic molecular theory that we need to look at, we're looking at a random motion of particles. And we're only going to look at gas particles for right now because this is the gas law chapter. They have very small attractive or repulsive forces between the molecules because part of the kinetic molecular theory is saying that the gases are so far apart and they are moving all the time that they don't have time to really interact with each other. And so they're moving so fast, maybe bouncing off of each other, that they don't have time to have any sort of attractive or repulsive force between them. They occupy a much larger volume than the volume of the molecules alone. This means that 99.9% of the container is empty space, and so we can pretty much say that the volume of the particles is 0. And now, just like electrons don't have mass, but they really do have mass, we can say the particles don't really have a volume, but they really do. It's just that they're so small in comparison to the volume of the container, the space available, that we say that their volume is negligible. They're in a constant motion, moving rapidly in straight lines, and this constant motion means that they're hitting each other and they're hitting the walls of the container, creating a pressure. And then if you have a Kelvin temperature, you are proportional to the average kinetic energy of the molecules. And so looking at the different properties that we're going to talk about when we talk about gases, we're going to talk about pressure, volume, temperature, and amount. The pressure is the force exerted by a gas against the walls of the container, and we have a bunch of units of measurement of pressure. We'll talk about that later. Volume, you're familiar with, the space occupied by a gas. Usually your volumes are going to be liters, milliliters. Your volumes could also be cubic length, cubic centimeters, cubic meters, any length cubed. The temperature is the energy, the kinetic energy, and the rate of the motion of the gas particles. Typically, we record temperature in Celsius, but you must do Kelvin in your calculations, and I'm going to say this a bunch of times when you're working on this. You cannot use Celsius in your calculations because a Celsius scale is not a zeroed out scale. And so you can have a negative Celsius temperature. Can you have a negative kinetic energy? No. And so when we're doing math with these numbers, you would put a negative Celsius in, you would wind up with a negative pressure, a negative volume, negative space. That doesn't make any sense. And so you need to use Kelvin because it is the only temperature scale which there's no negatives, where 0 means no energy at all. And so we must use Kelvin for calculations. So you must use Kelvin for calculations, and I'm specifically putting K's in that word. You must use Kelvin for calculations. Then the last thing we're going to look at is the amount, and we're looking at amount could be grams, but I really want you not to think about it in grams. Moles is what you're going to be using in your calculations. So one thing about gases is they're compressible. Because they have so much space around the particles, we can really compress the particles down, and that's going to help us think about the changes in pressures and volumes and things like that, versus liquids are not compressible. Gases also hit the walls of the container, and so every time I hit the wall of the container, I'm creating a pressure. And so your tires in your car, your bike, they all have some sort of pressure that they need to maintain, the gas pressure in there, because the particles are pressing up against the sides of the container. How far apart are gas particles? And thinking about this is kind of hard. If you were to take 1 can of soda and turn it into, boil all the liquid in the soda, it would take up 1,700 cans of soda. So from 1 to 1700, that's the difference in the particles of a liquid and the particles of a gas. So we talked about this before, but pressure is just hitting the walls of the container. And you can measure pressure in a few different ways. I want you to think about pressure in atmospheres, millimeters of mercury, or torr. But I think the most interesting one is PSI, because pounds per square inch is maybe what you're familiar with. If you look at your car tires, it's usually about 44 PSI. That's the max pressure that you should be putting in your tires. Now, when you're standing anywhere on the earth, you have a certain atmospheric pressure pressing down on you. And so at sea level, which is where we are in Santa Monica, at sea level, your atmospheric pressure is 14.7 psi, which means 14.7 pounds per square inch. The atmosphere is pressing down on you with almost 15 pounds per square inch. And so we are very strong to be able to hold ourselves up in this atmosphere because we're born into this, we're used to it. And, changing your atmosphere would affect kind of how you move through space, because now it's harder to move around or easier to move around. And so people train at different athletes train at different atmospheric pressures, but also because there's less oxygen in certain environments, and so they kind of give themselves a stressful situation so they can do better in oxygen-rich environments. And so the molecules in air are not 100% oxygen. 78% is actually nitrogen, and then 21% is oxygen and other gases. It depends on the cleanliness of your air, how close you are to water, right? If there's going to be a lot of water vapor in the air, then you get a humidity. But actually most of the atmosphere is nitrogen, not oxygen. And so going back to this beginning problem with the straw, how does a straw work? So first of all, the atmosphere is pressing down on everything all the time, including the liquid in this cup. And so the atmosphere is pressing down 15 pounds per square inch on this liquid. The atmosphere is also pressing down inside the straw. So when no one is sucking in the straw, you find that the atmosphere is pressing down equally on all sides. Now, if you lower the pressure in the straw, you're not sucking the liquid up. You're removing the gas particles from the straw, and you're making the pressure inside lower. So you're making like a vacuum. So the pressure outside is higher than the pressure inside, and that pushes the liquid up the straw. And so when you suck on a straw, you're not sucking the liquid up, you're removing the gas, and the atmosphere is pushing the liquid up into your mouth. We did a test, someone did a test to see if you had a perfect vacuum pump in which your mouth is not capable of doing that. But if you have a perfect vacuum pump and you had no particles of air in this vacuum area here, you could get 10.3 meters of a straw of liquid sucked up based on the atmospheric pressure of 14.7 pounds per square inch. And so could the kid have a straw this long? Sure, I'm sure he's probably not 10 meters tall. But this is a case with a perfect vacuum versus, his little lungs. Probably not capable of doing something like this, but theoretically it could be done. And so also thinking about pressure, you may have experienced weird pressures in your ears before. And a pressure is a force over area. So if you wear any sort of heeled shoe, you've maybe noticed that you feel more pressure on your feet because your force is related to your mass and acceleration, which is gravity pulling you down. And so your weight is kind of your force on the earth, and then the area is, well, how much area is touching the earth. And so when you're flat-footed, you've got a distribution of force, meaning less pressure. But if you are standing on your toes or standing in heeled shoes, then you feel more pressure on that area because there's less area and the same force. If you change the amount of gas in a closed container, you will have higher pressure because you'd have more gas pressing on the sides of the container. So that's what this slide is showing you. Units for pressure. You have all the conversions for all of these units of pressure on your periodic tables, so please do not worry about memorizing them. Just recognize what kind of units are pressure units. Typically, if you know that N is for moles, and you know that V is for volume, and you know that T is for temperature, the other unit is probably pressure. It's the weird unit, the ones you haven't really seen before. So your ATM, your atmospheric pressure, your millimeters of mercury, your torr, and your PSI are going to be the ones we use the most. Now, millimeters of mercury, what does that mean? That actually is how we use a barometer. A barometer has mercury in it. The atmosphere pushes down on the mercury. And then how high the mercury goes, that is literally measured in the millimeters of how high the mercury goes. And so here's some more conversions. Again, you will have this on your periodic tables. And so sometimes if you're riding in an airplane, we are pressurizing, well, we always pressurize the cabin because you want to maintain a certain percentage, that good 21% oxygen. Now, if the percentage, if the total air pressure goes down, well, the oxygen percentage goes down too. And so now we don't have enough oxygen to breathe. So that's why the oxygen masks will come down in the case that the pressure is messed up in the cabin. And so we'll talk about this in class a little bit, but you're going to have different gas laws and different relationships that you need to know. I'm not going to have you memorize individual names like Boyle's law, what is Charles's law, but you need to know the relationships. And so if you are talking about pressure versus volume, if you expand something, there's less room, there's more room, so it takes longer to get to the walls of the container, so your pressure is lowered. And so pressure and volume are inversely proportional. And this is how we breathe. And we'll talk about this in class, but you increase the volume of your lungs by moving your diaphragm down, and then you create a low pressure system inside of your lungs. The atmosphere pushes the air into that low pressure system to equalize the pressure and fills your lungs with air. Exhalation is the opposite. Making your lungs smaller increases the pressure in your lungs, and your air in your lungs exits to try to equalize the pressure. So we breathe because the air particles flow from high pressure to low pressure. Charles's law is another law. Volume is proportional to temperature. So volume and temperature are directly proportional, meaning one goes up, the other goes up. If you heat up particles, the volume increases. If the volume increases, the volume increases, the density decreases. If the density decreases of like something like a hot air balloon, it will float because now it's less dense. So heating up these particles cause it to move faster, and the particles moving faster then are going to have a larger volume because they're expanded, right? They're taking up more space, and then their density is going to be low, so the balloon will rise. Gay-Lussac's law is talking about pressure and temperature. So if you increase the temperature, then your pressure is going to increase because your particle is moving faster. If they're moving faster, then they're hitting the walls of the container harder. So this is a direct proportionality, pressure to temperature. Avogadro's law talks about moles, of course, and so if you add moles to something, the volume increases. And so this kid is blowing moles into a balloon. The balloon's going to get bigger because the volume is increasing. So Dalton's law is your last law. It is the law of partial pressures. And Dalton is pretty simply saying your total pressure is equal to your partial pressures, and I do A, B, and C, added up. And so if I wanted to find the total pressure in the lungs, well, the pressure of oxygen in the lungs, or the alveoli, and the pressure of the carbon dioxide is 40. So together in the alveoli, the pressure would be 140. So that's the total pressure. Inside your lungs and outside your lungs, the pressure tries to remain the same, which is how we breathe. And so you'll look at, you can kind of add these numbers up. And there's a table that kind of helps you look at this and it all adds up to atmospheric pressure 760. It's just different proportions, right? So different partial pressures. We have all these different gas laws. We're going to combine them into one law called the ideal gas law here, and we're going to rewrite this as PV equals nRT. R is a constant, and you will have that constant. It is 0.0821. I think you may have 0.08206. Either one is fine to use. Liters times atmospheres, moles over Kelvin. This is the unit of R. Do not plug numbers into that. We plug numbers into the variables, not to the units of R. R actually goes right here. R is just a proportionality constant. So you'll just plug R in like you would plug in any other number for a letter variable. The combined gas law is essentially solve for R. So if I were to take the ideal gas law and solve for R, R is equal to PV over NT. That's what I get. And so you don't have your N's there. You can write them in. We don't typically use N's for most ideal gas law problems because the amount of gas in the container is typically staying the same while we mess with everything else. But you can put it down there. You've got Pivnert and you've got PV teeny, and that's going to help you remember those. Again, you don't have to remember these though, I mean honestly, because you've got them in the periodic table, so just know how to use them. One thing I find that students mess up all the time is not solving the combined gas law correctly. So please cross multiply your combined gas law before you plug any numbers in, and make sure you're isolating your variable first. And we'll go over this in class a little bit more. Okay, so looking at how might I deal with the Dalton's law of partial pressure. So a mixture of helium, neon, and argon has a total pressure of 558 millimeters of mercury. So my P total is 558 mmHg. If the pressure of helium is 341 and the pressure of neon is 112, what would the pressure of argon be, assuming that I only have those three? Well, they have to add up to the total pressure, so we've got to add up to 558 here, plus whatever the pressure of argon is. Okay, so I'll do 558 minus 112 minus 341 to get my pressure of argon as 105, and the unit here is millimeters of mercury. So that's how you would do a partial pressure problem. We talked about vapor pressure. You will not probably have vapor pressure problems, so if you want to skip this one, you can. Again, it's just the total pressure has to equal the parts, and so total pressure here, what would the partial pressure be if the total pressure is the water vapor and the hydrogen gas? So looking at this question, a sample of gas has an initial volume of 158 milliliters at a pressure of 735 millimeters of mercury and a temperature of 34 degrees C. If a gas is compressed to a volume of 108 mils and heated to a temperature of 85, what is the final pressure in millimeters of mercury? And so I'm going to identify my variables here. In initial volume, so I'm going to say I have a volume of 158, a pressure of 735 millimeters of mercury, and a temperature of 34 degrees C. Now do not let your temperature stay like that. Immediately turn it to Kelvin. So turning temperature to Kelvin, we add 273. And so I like to leave it just like this in my calculator, but you can add it up if you want to. If you did, it would be 34 plus 273, which is 307 Kelvin. That is not something that you can see. That's not any better. Nope. Sorry, hang in there. Okay, so this is 307. Don't let any gas law, your temperature cannot remain in Celsius at all, so just don't even let it sit on your paper like that. Now it gives me a gas is compressed to a new volume. So as soon as I see that's new, all of these now become my ones, my initial. And so now I'm going to write some 2's. And so I have a V2, which is 108, a P2, which is what is the final pressure, so I want to know what that is. Unit is millimeters Hg. And then you have your T2, which is again 85 plus 273, don't let it live. And you can do that conversion if you want to, 358 Kelvin. So I can see that I have 1's and 2's here, so I'm thinking I probably need to use the combined gas law. So remember, the combined gas law on your periodic table looks like this. But before we plug the numbers in, we're going to rearrange so that it says P2 equals some other stuff. So first I want you to cross multiply. So cross multiplying, these are going to go together on the same side, and these are going to go together on the same side. So you're going to get P1V1 times T2 equals P2V2 times T1, because you're going to make sure that these are all paired up across from each other. Now, it is so much easier at this point to identify what P2 is because you don't have a top and bottom. So because P2 is being multiplied by V2T1, it must be divided by the same thing, and you want P2 by itself, so don't divide the P2, divide everything else that's with it. So this will cancel, and then so you have P2 is equal to P1V1 T2 over V2 T1. And that is what the law is. When you next use it, you'll just plug all the information in. And so my P1 was 735. I'm running out of space. I'm going to do it to my units because I know they're going to cancel. My V1 was 158. And my T2 is 358. All over. My V2 is 108. And my T1 was 307. Start letting this catch up. I think my internet is not wanting to put everything together. Okay. And so I will set it up like this, and I will do my math. I have 735 times 158 times 358 divided by 108 divided by 307. And I get 1253.9, and I need to round this to 3 sig figs, so I need 1250 millimeters of mercury. And that would be my answer. All right. So that's how you would do a combined gas law problem. So I'm going to clear this so we have a little more space. And I'm going to show you how to do a different type of problem. And we're going to be doing lots and lots of practice with this in class. So just show you here how to do one type, and then we'll move forward. Let me show you, actually, if you would like to do number 2, or this one here, the calculated volume by 0.845 mole, go for it. The answers are in the speaker's notes of the slides, but I really would like to show you this one. So a sample of gas has a mass of 0.136 grams. Its volume is 0.112 liters at a temperature of 298 K, pressure of 1.06 atm. Find the molar mass. So this is kind of a harder question. You need to know what molar mass is. Molar mass is grams per mole. So I need two things. I need grams, I need moles. Do I have grams? Yes, I have grams. And so my grams are already given to me. I do not need to find them. I cannot find them because I don't know what the substance is, so I cannot use a molar mass unless I know a substance. So what am I missing? I'm missing moles. So can I find moles? So moles is N. N equals what? Look at what I'm given. I'm given a volume. That's a V. I'm given a temperature. It is already in Kelvin, so I don't have to do any converting. And I'm given a pressure. So I have V, T, P, and N. And so you should be thinking I will use PV equals nRT here because I have all of those letters except for one. Yes, you have R. R is given to you as a constant. Okay, so plugging in, before you plug in, hold on. Before you plug in, I would like for you to rearrange. We want to solve it for n, so n is equal to PV over RT, and then I can plug in. And so I'll say n is equal to 1.06 ATM. I'm going to show you the units for this one. 0.112 liters. Let's just, maybe this is... Okay, sorry, I think the calculator was slowing it down for some reason. So we have our N in our PV over our RT. So let's look at R. 821 liters times ATM. Wow, sorry. Over mole times Kelvin. Yikes. Times your T, which is 298. So we're going to do a quick canceling of the units. And so if I have ATM on top, it will cancel ATM on the bottom. Liters on top cancels liters on the bottom. And then on the bottom, I have Kelvin on the top of the bottom and Kelvin on the bottom of the bottom. So it cancels. I'm left with moles in the bottom of the bottom, which is really the top. And so that's kind of what I want. And so now I can do some math to find the moles. Whoops. Do some math to find the moles. And I get 1.06 times 0.112 divided by 0.0821 divided by 298. Okay, hopefully that fixed things. I restarted my program. So I wound up with 0.0048525. And that is your answer. We will be rounding to 3 sig figs, so you will keep these three numbers. 0.00, oh sorry, we're not, so we're not rounding quite yet, but we will box those sig figs because we will be using those numbers outside of the box in our next math. And so remember, I'm looking for the molar mass, and so I need to find the grams per mole. I need the 0.136 divided by 0.0048525. Use all those numbers, just make sure you're remembering that only 3 of them are significant. And then we get a final answer of 28.0 grams per mole. You can actually identify out of a list what elements or compounds that would be. Okay. There is another question here that you're welcome to go through and do. It involves a multimole ratio as well as some gas laws, and so I challenge you to give that one a shot. We will be looking at that one in class together. This last table that is slowly coming up. Sorry about that. If you had a weird thing happen, my program is not working very well. So we have a gas law summary here, and you don't have to worry about knowing each individual law. You'll have it on your periodic table. So our next slide is molar volume. This is one more conversion factor that you're going to have. Now, at this special conversion factor is like a shortcut where you may have to use the ideal gas law if you don't remember it. But if you remember this as a conversion factor, then you can skip the ideal gas law. So what this conversion is saying is that if you have conditions called STP, standard temperature and pressure, then 1 mole of a gas at that temperature and pressure is equal to 22.4 liters of volume. So you may go straight from moles to volume of a gas if you're at a specific temperature and pressure. If you're not at that temperature and pressure, you have to go through the full PV equals nRT. But if you are at STP, standard temperature and pressure, then you can do this shortcut and do a quick mole conversion using the molar volume. This should also be on your periodic table. So what this means is that if you have 1 mole, you have the same amount of particles, kind of, and so it should take up about the same volume because it's at the right kind of temperature. And so looking at our last question, we are going to do a quick problem calculating the number of liters of gas that forms at STP when you have calcium carbonate undergoing this reaction. So if I put in 0.879 moles of calcium carbonate, and I want to know how many liters of the gas that are formed. The gas that's formed here is carbon dioxide, and so I want to know liters of carbon dioxide. So I'm going to start my setup just like this and write some conversions. And so, well, first of all, if I'm changing substances, I need a mole ratio. And so I can see that 1 mole of calcium carbonate is equal to 1 mole of carbon dioxide. Because of the mole conversions, the dimension, the balanced chemical equation is all a 1-to-1 to 1 ratio here. And then I know that if I'm at STP, I can say 1 mole of gas is equal to 22.4 liters of gas. And so STP gives me this very special conversion that I can then use. And so setting this up, I'll start with 0.879 moles of calcium carbonate. Canceling moles of calcium carbonate. Thank you, Kona, for that head shake. Music to our video, I'm sure. He's my background music, his head shakes. Sorry. So sorry, this is the last slide. Just bear with me. Canceling our mole of calcium carbonate with mole of calcium carbonate. You can't really see that coming in down there. But this is mole of calcium carbonate down here at the bottom that I'm trying to fit in. And then it is equal to 1 mole of carbon dioxide. 1 mole of carbon dioxide is equal to 22.4 liters of carbon dioxide because of that special mole relationship. And so very slowly we'll be bringing this up. Now don't ever assume that you can do the 22.4 liter for something solid like calcium carbonate because you need to go to gas to do that. I know it's a 1-to-1 ratio, but you should still show that 1-to-1 ratio so you don't get it confused later when it's not a 1-to-1 ratio. So here's your setup. And so hopefully you have that and you can figure out how to set that up. It is just the same as we've been working before, just a conversion, and your answer is 19.6896 liters of CO2, rounding to 3 sig figs. Your 22.4 does not count for sig figs, it's a definition. I would get 19.7 liters of carbon dioxide here as my final answer. And you can keep watching to see it, or you can trust me that 19.7 liters of CO2 is your answer. So thank you for bearing with me. That is the end of Chapter 8. We'll see you in class.